All right. Hello, everyone. Today we're going to look at part two of Unit 1 and the areas of artificial intelligence or the AI family. All right, so let's begin by defining some scope. Artificial intelligence as a field. So, as we've already discussed, AI is a very broad field of study that creates machines that perform tasks that require human like intelligence with the goal of simulating or replicating human intelligence behaviors. But AI is not just robots, it's any system mimicking intelligence, understanding language, recognizing images, playing games, and making decisions, like self driving cars or chatbots or chess games or even autocomplete on the internet. One analogy is like the Russian dolls analogy, one doll that nests inside of the other doll. So the outer doll, the broad field of artificial intelligence, has within it machine learning, which is a subset of AI, which has within it deep learning, which is a subset of machine learning and therefore a subset of artificial intelligence. Many of us focus on models like ChatGPT and Gemini. These are deep learning models, but this is just one aspect of artificial intelligence. For example, everything in deep learning is not AI, but not all of AI is deep learning, as AI is not one technique, but a collection of approaches and subfields, which we have seen in this diagram in part 1 of this unit. Machine learning is a subset of AI, like thermodynamics is a subfield of physics. Deep learning is a subset of machine learning, and therefore a smaller subset of AI. And neural networks are used by deep learning, and therefore another subset. Within deep learning, we can have various models of implementation that we looked at in part 1. The discriminative model, the generative model, the large language model, and existing AI systems like Gemini and ChatGPT, they fall somewhere in the intersection between generative and large language models. And within deep learning, we have the neural network, which is a machine learning system inspired by the human brain. So this gives us an idea of all the fields and subfields within the broader term of artificial intelligence. So let's now move on to look at the systems in artificial intelligence. In 1950, Alan Turing, an English mathematician and a computer scientist, who we've seen in the movie The Imitation Game, devised a test called the Turing test. Basically, the Turing test is a benchmark designed to see if a machine can exhibit intelligent behavior that is indistinguishable from human behavior. In other words, it can imitate a human. If a human evaluator engages in a conversation, whether that is text based or verbally, with both a machine and another human, and it cannot reliably tell which is the machine and which is the human, then the machine is considered to have passed the Turing test. It remains one of the most famous and debated philosophical hurdles in the field of artificial intelligence, shifting the focus from whether a machine can think to whether or not a machine can successfully imitate a human in terms of thinking. So, this is the general summary of the Turing test by Alan Turing, proposed originally back in 1950. The limitations of the Turing test is that it measures imitation, not true understanding. It focuses on conversation, giving us, the humans, what we want, and does not really test reasoning or perception or physical interaction. A machine might pass by being very deceptive or mimicking human errors rather than being truly intelligent. So, like this test with its rules, early developments in AI were designed as rule based systems. Those rule based systems, sometimes called symbolic artificial intelligence, they follow instructions, typically code, things like an if then statement to provide those instructions to the AI system. The limitations of the rule based system is that it can be illustrated with the self driving car. If we used a bunch of code that wrote if then statements, a rule based system, a traditional programming style for AI for self driving cars, the self driving cars would not be effective because driving has infinite unpredictable scenarios, such as weather and pedestrians and construction and human behavior. They do well in that predictable environment. The rule-based system likes consistency. It's impossible to write all the rules for the infinite number of edge cases that driving cars would encounter. We have very limited flexibility within a rule-based system. And these systems cannot adapt beyond their rules. So AI systems can't be rule-based if we're talking about self-driving cars. They have to learn patterns. They have to perceive, they have to generalize, and not just follow a rigid set of rules. So many modern AI systems are not rule-based. They're learning-based systems. They use massive amounts of data and they improve and learn with performance. They look for and find patterns, and they can and are adaptable to handle more uncertainty and more variation. They're used in things like speech recognition and computer vision, and obviously, why we use this example, in self-driving cars or autonomous vehicles. For example, learning to identify a cat by seeing many different examples of cats, not memorizing the strict definition of what a cat is in a rule-based system, would be more effective. For example, if it has whiskers and it has pointy ears, then it is a cat, could easily fail. All right, so let's move on now to the concept of machine learning. So machine learning can be summarized as using a computer program to take input data and train a model. And then that trained model can make predictions with new data it's never seen before through learning. Machine learning uses uses these programmed algorithms to analyze large data sets, to learn, to find patterns, to make informed decisions by improving performance over time. Some machine learning techniques include the supervised learning model, which trains or learns on what's called labeled data. This is data that has a very clearly defined output label and examines the outputs to match the data. So note, the term labeled data consists of like raw data like images or text or audio that has been annotated or provided a tag or a label to provide context and meaning. This process, called data labeling, turns data into input-output pairs so that when the model gets the input, it can use the label to determine did it have the correct output. So for example, if you feed it an image of a cat that's labeled cat, did it predict that it was in fact a cat? Continuing this technique, we have also unsupervised learning models. These train or learn on unlabeled data to recognize patterns. So this is data that does not have a label explaining what it is. They learn patterns or structure within the data. So here you see an analogy of a graph of years working at a company versus the income that employees receive. And obviously, as the years go up, the income could go up. But this is unlabeled data, right? It's raw data within the scatter plot. We don't know much of the data other than where it falls on the axes. Versus labeled data, which is color-coded within the scatter plot. For example, in this chart, we see the total bill amount versus the tip amount. So obviously, if you have a high bill at a restaurant, you might expect a high tip. But now the data is also labeled between restaurant orders that were picked up versus restaurant orders that were delivered. So now we have labels on the data within the scatter plot. It's the color coding. And then finally, we also have reinforcement learning. This focuses on training agents with the goal of like getting a reward or maximizing a reward signal, perhaps providing penalties. This will guide the learning towards the specific goal or outcome that we want. So these algorithms, this programming in machine learning, uses statistical models to find the patterns in the data. And let's summarize the steps of machine learning. 1, data is fed or trained into an algorithm, both supervised labeled data or unsupervised or unlabeled data. 2, the algorithm will identify a pattern and a relationship using statistics and statistical models. In other words, this is the learning, where it learns the patterns. 3, Based on those patterns, the algorithm creates a new learning model, or it modifies or reprograms itself, or relearns the correct pattern. This new or adapted model is then used to make predictions or decisions on new unseen data. And as the new model gets data and it gets the feedback on how successful or not successful it was, it refines its performance by going back to step one in an iterative looping process. Now, we're going to examine this in more detail throughout the course, but this is the general 5-step process of machine learning. All right, now this leads us to the subset known as deep learning. So with deep learning, which is a subset of machine learning, we utilize complex artificial neural networks, which again, we're going to examine in more detail, and train on large data sets, both supervised, unsupervised, and semi-supervised. The more layers in the neural network, along with the size and variety of data that it's going to train on, will determine how powerful or how deep that learning model is. Deep learning models can also be divided up into discriminative or generative or large language models. Discriminative models learn from the relationship between the labels of data points and can classify those. For example, a large set of bank transactions could be labeled as fraud or not fraud, and the discriminative model will learn how to identify those transactions so that it can discriminate and predict, is this a fraudulent transaction or not a fraudulent transaction? So the deep learning discriminative model trains on that labeled data. Another example might be to train on learning a discriminative model on, say, a set of pictures of cats and dogs that are labeled cat and labeled dog. Then you input into that deep learning discriminative model a new data set. So a picture of a cat, and see if it can predict using probabilities, using decision boundaries, what label to put on this. Should it label it a dog or not a dog, or cat or not a cat? Generative models learn about patterns in the training data. So when a generative model is given an input, for example, a prompt from a user, it generates something new based on the patterns that it has previously learned. For example, if it's trained on unlabeled data of pictures of cats and dogs, the generative model will start to learn the patterns in the pictures. So then it will use those patterns when it's asked or prompted to generate something completely new. Like, for example, a picture of a dog, and it will use the patterns it learned for dogs to generate that new image. Large language models, or LLMs, although there is overlap, LLMs and generative AI models are not the same thing. Although we do have models like Gemini and ChatGPT doing just generative AI, they are also large language. Large language models are pre-trained with large set of data, specifically fine-tuned for specific purposes. They're pre-trained in things like text classification, answering questions, summarizing documents, and text generation. LLMs can then be fine-tuned to solve specific problems. For example, they can be put specifically into retail problem sets, or finance, or healthcare, or entertainment. So the LLM can be fine-tuned for that specific task. Various AI models are developed and then sold for specific purposes. For example, smart car hardware, or to websites, or hardware like Alexa, or Google Home, or Apple Watches, etc. So that most common AI model, the ChatGPTs, the Geminis, the Copilots, the Claudes, those intersect between large language and generative. In other words, they can do both. So large companies that have billions of dollars in resources can train these huge large language models and sell them to companies with specific data sets for fine tuning. So here's a way you can tell. Is it not or generative? Well, if the output is a number, or a classification like spam or not spam, or a probability value like, say, 38%, then it's probably not a generative model. How can you tell if it is a generative model? Well, if the output is something like language, like text, like please write me an essay, or an image, please create me a picture of a dog, or audio, the generative model generates new data that is similar to the data that it was trained on. So text to text, taking natural language in and producing text output. This is a very common use of ChatGPT, Gemini, and Claude. Text to image, where we train on large sets of images and then generate new images. Midjourney is an example of this. Text to video, where we can generate and edit videos. Text to 3D models, producing 3D models for gaming assets or 3D printers. Text to task, training to perform a specific task or action based on text input. All right. Thank you very much, everybody. That was part 2. I hope you enjoyed that and I hope you learned lots. And have yourself a great day.